it is. Okay. I'm going to work with it with my shared screen because it's a little bit faster and I would like to go through this exercise with you guys a little faster so we can move on to the inverse. So exercise 2.9 gave us this system of equations described by x1, x2, x3 is equal to 4. Sorry, x1 plus x2 plus x3 is equal to 4. 2x1 plus x2 minus x3 is equal to -1. And x1 minus x2 minus x3 is equal to -2. And again, I have to start by trying to eliminate x1 from the rows which do not contain its indices. The same thing for x2 and the same thing for x3 in this specific order. When I look at the system first, I notice a problem with the second row because it contains way too many x1s. It contains 2. So my initial thought when I see such a coefficient is to try to eliminate that first. So I could have either done row 2 minus 2 times one of the rows 1 or 3, or because I like to complicate a little bit my life sometimes, I decided to write a row 2 minus row 1 minus row 3 just to see what happens. So that's exactly what I did. In this second parenthesis here, you can see the result of what I had done. Rows 1 and 3 are completely unchanged. The only thing that's changed is row 2. Let's see how. From the second row, so 2x1, I have eliminated 1x1 minus 1x1, that would come up to a total of 0. Plus, I have x2 minus x2, that is 0, minus x2, that is positive x2. Then I have minus x3 minus x3, that is negative 2 times x3, minus, that is a plus x3. I come up to a total of minus x3. It is equal to -1 minus 4 plus 2 minus 3. So now I have this new system. I look over it again. I see that I have one more x to eliminate. So I decide to do row 3 minus row 1. It's the only operation I can do in order to eliminate this x1. So when I conduct row 3 minus row 1 and row 2 do not change. The only changes I'm going to make are on row 3. How? x1 minus x1 will come up to a 0. Minus x2 will become negative 2 times x2. Minus x3 will become negative 2 times x3. It is equal to -2 minus 4, which is a -6. And this is the third row as it is. I decide further on to divide this row by 2 because I see everything is divisible by 2. So I come up to the exact version of the system from earlier, only this time I've multiplied the second row with the third row by a 2, so I come up to an easier form. Moving on. Now that I have eliminated my x1s, I start eliminating my x2s. And the easiest elimination I can do right now is by adding to the third row the second row. Why do I add it and not subtract it? Because my x2 here has a negative sign in front of it. So in order to get rid of it, I need something positive. So I'm going to do row 3 plus row 2. Again, row 1 and row 2 unchanged. The only changes I make are on row 3. So 0 remains 0. Minus x2 plus x2 will also become a 0. Minus x3 will become a negative 2 times x3, which will be equal to a -3 minus 3 minus 6, meaning that my x3 will become a 3. And like I've told you before, I try to keep this x3 as a row, as a row in my system, just for the sake of it. So I come up to this system, which I can, from here on, reduce, like we've done before when I told you we're not being good students. I know x3 is equal to 3, and I know this equation is only dependent now into x2. I can transform it into x2 minus 3 is equal to -3, which means that my x2 will become a 0. If I know that my x2 is a 0 and my x3 is a 3, I can move on to the first line of the equations, and I can deduce what is x1 by writing down all of the coefficients that I already know. So x1 plus 0 plus 3 is equal to 4. Therefore, my x1 will be equal to 1. So my final solution x, my vector x, will become vector 1, 0, 3. And this is how we do exercise 9. Is this a little bit more clear now? Does it make a little bit more sense? Do we all understand how to do it now? Yes? Okay, perfect, guys. Yes, I have already. If you didn't get it, text me privately so I can send it again, so I don't send it many times in the group chat. If you didn't join already the WhatsApp chat from before. So text me privately so I can send it again, because I will send everything over there. Okay, great. I hope we all understood. Oops, taking a few steps forward from you guys. So I hope we all understood systems of linear equations, because now we have to move on to something even more interesting, which is called the inverse of a matrix. So the inverse of a matrix, again, we come back to the matrix. So we switch from matrix to system, and now we come back to matrix. Because in order to determine the inverse of a matrix, we actually need to know the operations done in the row reduction procedure on the system of linear equations. You will see in a second how. So let's speak a little about the inverse first, understand the theory behind it, and then we'll move on. So what is, before jumping into the inverse, we need a few more information about, a few more notations, I would say, about what is a non-singular, what is a singular matrix. So we call a matrix or a system of equations non-singular if it can be reduced through the row reduction procedure to the corresponding identity matrix. Do we all remember what the identity matrix is? Is the matrix that contains only the numbers 0 and 1, where the 1 is always positioned on the diagonal of the matrix. So from top left, bottom right, that is a line of ones. Sorry, a diagonal of ones. That is the identity matrix. Therefore, a matrix will be called non-singular when I will be able to reduce it through the row reduction procedure into an identity matrix. Maybe you're now going to ask me, but how do we reduce a matrix using the row reduction procedure? Well, remember that the matrix represents the rectangular representation of the coefficients of the system. Therefore, I can actually apply row reduction both on the matrix and on the actual system, because nothing really changes. Only when we work directly on the matrix, in my opinion, it is a little bit easier because we only work with the coefficients, so we never have to worry about the x's. We will see in some exercises later on, because this is the method we're going to start working with now. But yes, this is how we work with row reduction. This is why we can work with row reduction on the matrix as well. So this is what a non-singular matrix is. Can you guys guess what a singular matrix will be? If a non-singular matrix can be reduced to the identity matrix, a singular matrix is something that cannot be reduced to that. So it's a normal matrix that through row reduction procedure, we cannot get to the identity matrix. That's it. Let's look through some properties. For a non-singular system, we know that the equation, so Ax equal to b, this is the equation of a linear system, has precisely one solution for any choice of b. So if we know that our matrix A is non-singular, it means that my system will have one solution only. On the other hand, each singular system has either no solution or infinitely many solutions. Little bit of theory. What about a homogeneous system? Remember, a homogeneous system was this type of system where Ax is equal to 0, where 0 here doesn't represent number, but the null vector, so a vector which contains only the elements 0, 0, 0. So a homogeneous non-singular system, so a non-singular system that is equal to 0, has precisely one solution, which is x is equal to 0. a homogeneous singular system can have infinitely many solutions. Again, a little bit of theory that we have to understand for the exam. We have to remember it. Could be a theoretical question. I'm not super sure, I cannot know for sure, but it's a little bit of theory that could possibly appear in the exam. So it's really good to remember. Now that we've talked a little about this notation of singular, non-singular, homogeneous, non-singular solutions and so on, we can actually get into the discussion of the inverse of the matrix. So we will call a matrix B the inverse of matrix A if and only if B and A satisfy these equations at the same time. So A multiplied by B is equal to B multiplied by A, and in total, they give me the identity matrix. So the multiplication between the two is equal to the matrix which has a diagonal of ones. If the equation is true, matrix A can be called invertible because it has an inverse. The notation of the inverse of a matrix is the matrix to the power of -1. Therefore, A to the power of -1 will be the inverse of A. Be very, very careful that an invertible matrix has precisely one inverse. It means that there exists only one matrix A to the power of 1 that can be the inverse of A. Moreover, any non-singular matrix, so any matrix that can be reduced to the identity matrix, has an inverse, and any invertible matrix is non-singular. So if a matrix has an inverse, I know it is non-singular. So it's a two-way street between these two parts of the sentence. And now I wanted to practice with you and actually show you how we calculate the inverse of a matrix. Because again, I believe the actual representation will be a little bit more efficient than me just rambling on with theoretical points. However, 2.14, exercise 2.14 is a great exercise. However, it's for you to do as homework because it only speaks about the singular versus non-singular matrix. The same for exercise 2.15. And we will work together exercise 2.18, part A. Because it's a great exercise to start with, and it allows us to work with row reduction directly on the matrix. So we will work exercise 2.18 from the book, which is, where is it? Oh, sorry, I don't know what I did. Where is, okay, here, this one. So it's exercise 2.18, part A. We have to determine, if possible, the inverse matrix of my matrix A, which will be the matrix. I'm going to read the rows: 1, 3, -2, 2, 5, -3, -3, 2, -4. So this is the inverse, the matrix that we have to try to inverse. I'll give you guys another minute just so I can make sure that you can write the matrix yourself. Afterward, like before, I'm going to switch to my whiteboard and we'll move on. For time-saving reasons, I will also take a picture of the exercise so you guys can see how we do it later on. Okay. All right, great. Let's move on to the whiteboard. So my matrix A will be equal to So I'm going to write the rows again. 1, 3, -2. Then I have, then I have 2, 5, -3. And the last row, -3, 2, 4. I hope I wrote it down correctly. Let me check once more. 1, 3, -2, 2, 5, -3, -3, 2, -4. Yes. Oh, -4. See? Now it should be correct. And now we have to find the inverse of this matrix. Now you're going to understand why a non-singular matrix is invertible, and any invertible matrix is non-singular. Because in order for us to determine the inverse of a matrix, we have to create an extended matrix of coefficients, which includes now the identity matrix. So first step, create an extended matrix with the identity matrix, with the corresponding identity matrix, right? Because I have a 3 by 3 matrix, it means that my identity matrix will also be of 3 by 3. So it will look like 1, 0, 0, 0, 1, 0, 0, 0, 1. Again, first step, create the extended matrix with the identity matrix as an extension. So how should this look like? It should look, I'm gonna write like that, like this. I'm gonna write my matrix A as normally, only I'm going to extend the rows with the identity matrix. So I'm gonna do 1, 3, minus 2, 1, 0. Maybe I'm gonna put more spaces between them because I can. 1, 0, 0. Then I have 2, 5, minus 3, 0, 1, 0. And my last row, minus 3, 2, minus 4, 0, 0, 1. Like that. This is what we call the extended matrix, which is extended with the identity matrix. Is literally my matrix A here to the left, and to the right, inside the same rectangular shape, I have the corresponding 3 by 3 identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And now I'll tell you the purpose of this creation. So the purpose is to inverse the two matrices. But how do we do it? We cannot just simply take the identity matrix and put it to the left and then take this part of the matrix and put it to the right. That's not how it's done. It is done by doing a row reduction procedure. So by doing the row reduction procedure, the left side of my matrix, so this side right here, this side, through row reduction, left side has to become the identity matrix through the row reduction procedure. So do you remember earlier when we worked with the systems, we had subtracted the x's, x1, x2, and x3 from their corresponding from the not corresponding indice lines. Remember, x1 had to be on row 1, x2 had to be on row 2, x3 had to be on row 3. It's because of this reason. If all of the other coefficients are 0 and all that's left is x1, x2, and x3, it means that those x's have the coefficient 1 in front of them. Therefore, when you create them into a coefficient matrix, the corresponding matrix that exists is actually the identity matrix. That's the logic behind it. And that's what we're about to do right now. How are we going to apply row reduction on the matrix? Exactly like we did with the systems, only we don't have the x's. So we only work with the coefficients, which in my opinion, it's actually even easier. So we will begin. How do we begin? By doing the first operation. I'll change the color of the pen first. Doing the first operation of the row reduction procedure, I'm going to ignore this. So what I have here is ignore, okay? Right now, ignore. I don't care about it because things are gonna change around here, but I don't care about those changes because all I care about is creating this, transforming it into an identity matrix. So that's what I'm gonna do. So I'm going to start. The first operation that I think I could do, I see here kind of a connection between this -3 and this 1 and this 2. I know that if to the third row I would add row 2 and row 1, this -3 would disappear and it would point me to a 0, which is exactly what I need. So that's what I'm going to do. I'm going to do row 3 plus row 2 plus row 1. And I'm going to obtain row 1 and row 2 again remain unchanged because I'm not going to make any changes to, I'm not going to do any changes to them. Only the third row will become affected in the future. So 1, 3, -2, 1, 0, 0. Then 2, 5, -3, 0, 1, 0. And now the row that has become the changed row, row 3 plus row 2 plus row 1. -3 plus 2 plus 1 will become a 0. 2 plus 5 plus 3 will become a 10. -4 -2 -3 will become a -9, I think. 0 plus 0 plus 1 will become a 1. 0 plus 1 plus 0 will become a 1. 1 plus 0 plus 0 will become a 1. This is the first change that we have done to our matrix. We have already obtained the first 0. What's the second thing, the second procedure we can do? We have to look around and try to find other connections between the lines in order to further create zeros. And again, we should keep in mind that we always subtract or try to eliminate first the x1s and then the x2s and then the x3s. So keeping that in mind from the row reduction from the linear systems, I should somehow get rid of these 2 now. So the only operation I can do on the second row in order to eliminate these 2 is by subtracting from the second row 2 times the first row. So 2 times row 1. I can do this. I can do anything I want because it works, because it's correct. So why am I subtracting from row 2 times row 1? Because I need to create this 2 into a 0. Therefore, I need something like a 2 to subtract it with. I can obtain it by creating it as 2 multiplied by the first row. However, am I actually going to multiply the first row by a 2? No, I don't need to. I can leave the first row intact and simply just keep in mind that when I'm going to do the subtraction, the first row will be times 2. So 1, 3, -2, 1, 0, 0. This is my first line, which again is unchanged. Now my second line will have changed as row 2 minus 2 times row 1. So 2 minus 2 times 1, that will become a 0. 5 minus 6 will become a -1. -3 minus 2, that will become a -3 plus 4, that's a 1. 0 minus 2, this is -2. 1 minus 0 will remain 1, and 0 minus 0 will remain 0. And now the third row is unchanged. I didn't do anything with it. So I'm just going to write it as it were before. 1, 1, 1. Moving on. Oh, okay. This is already a lot more exciting than what we used to do before. Now, I have eliminated all the x1s, theoretically, from the second and third row. I can move on to x2. So I can start eliminating x2s. And the only solution I would see that would be easy also from a computational point of view would be using the second row on which I have to keep the 1 in order to eliminate this 10 and this 3. So what I'm thinking of doing is first eliminating this 10 right here. It is pretty big, so I'm going to work with the third row, row 3. And I would like to eliminate this 10 completely, but how? I have here a -1. Therefore, if I were to multiply this by a 10, I would get a -10. If I do -10, if I do 10 minus 10, I would obtain a 0. So I think that's the operation that I should do. Therefore, to the third row, I'm going to add 10 times row 2, sorry, 10 times row 2. Again, why do I add? Because I have a negative sign here, so through addition, I'm actually keeping the negative. And again, the matrix. Row 1 is not changed, so I have 1, 3, -2, 1, 0, 0. Then I have row 2 is not changed, 0, -1, 1, -2, 1, 0. And the third row, to which I'm going to change, to make changes now, will be 0 minus 10 times 0, that is 0. 10 minus 10 will become 0. -9 plus 10 will become a 1. 1 minus 20 will become -19. 1 plus 10 will become an 11. And 1 plus 0 will remain a 1. This is amazing. We've already created a 0, 0, 1 on the last line. We don't have much to go from here. But we're on the right track because as we can see, we have already created a lot of zeros and a lot of ones, which is exactly what should happen. What happens next? The next operation that I am thinking of doing. Well, ideally right now would be to also get rid of this 3 right here so I can obtain another 0. So from the first row, now I'm going to make changes to the first row. I would add the 3 times the second row. So plus 3, row 2. Again, I do this in order to get rid of this 3. And why can I do this? Because adding 3 times the second row to the first one does not change at all the position of my 1, because here I have a 0. So 0 plus 1 will remain a 1, which is exactly what I need, because I need to create the identity matrix. And that is the position of the 1 that I need in my identity matrix. So first line will be changed. How? Row 1 plus the 3 times row 2. 1 plus 0 will remain a 1. Then I have 3 plus 3 times -1 will become a 0. Then I have -2 plus 3 will become a 1. 1 minus 6 will become a -5. 0 plus 3 will become a 3. And 0 plus 0 will become a 0. And I hope I didn't make any calculus mistakes. If I had, however, let me know. Second row unchanged, so 0, -1, 1, -2, 1, 0, and 0, 0, 1, -19, 11, 1. Great. What is the next operation I should do? I would like actually to copy this, but I don't think I can. So I'm going to write it down and write it again on the next page of my, where is it? I'm going to write it down on the next page of my whiteboard. Okay, so I'm going to write it down again here so we can all see it more clearly. So it is 1, 0, 1, -5, 3, 0, 10. 0, minus 1, 1, minus 2, 1, 0, 0, 0, 1, minus 19, 11, 1. Great. What's the next thing that I should do logically? Well, I need to further create 2 more zeros. I need to create a 0 here and a 0 here in order for this to almost become the identity matrix. So I'm going to make use of the third row, and I am going to subtract row 1 minus row 3, and then I'm going to do row 2 minus row 3. I can also do it at the same time in the same equation. I don't want to confuse you. If you think that is the way too complicated, you should do it step by step. We can also do it at the same time. So we can do row 1 minus row 3. And at the same time, I will do row 2 minus row 3. Like that. And the result of what I obtained will become the matrix with 2 rows changed this time. So first row will be changed, will become 1 minus 0, 1, 0 minus 0, 0, 1 minus 1, 0. That is great. Then I have minus 5 minus 19. That is, I think, plus 24, if I'm not mistaken. Wait. Am I mistaken? No. It's minus 5 plus 19. That is 14. I'm sorry. I don't know what I was thinking, right? I think it's 14. Then is 3 minus 11. That should be minus 8, I think. And 0 minus 1 should be minus 1. I think this is correct, right? Yes. I'm sorry. Sometimes I get a little tired. What did I do here? Minus 8 and minus 1. Okay. Second row will remain. Will become 0. Minus 1 minus 0 will remain minus 1. 1 minus 1 will become 0. And then here I have minus 2 minus 19. So minus 2 plus 19, that is 17. 1 minus 11 is minus 10. And 0 minus 1 is minus 1. I think that should be fine. And the last row, the third row, is the one that we made modifications with. So nothing changed. Minus 19, 11, and 1. So I've gotten to this stage of my matrix, which is great. However, it's still not exactly quite the identity matrix. Why? Because of this minus 1 right here that is accommodating us. In order for this to be identity matrix, this minus 1 should have actually been a 1. So what I can do is I can multiply only the second row with a negative 1 so that this becomes a positive. Why can I do that? Because when we're thinking about these matrices now, you have to think about them in a system form. In a system, can you multiply and subtract anything, add anything? Yes, you can, as long as you do it to the both sides of the equation. So if I'm going to multiply a minus 1 here, it means that also the signs of this part of the equations will be changed as well. Which makes me come up to my final matrix. The matrix 1, 0, 0, 14, minus 8, minus 1, 0, 1, 0, minus 17, 10, 1, 0, 0, 1, minus 19, 11, 1. And if I check, this is the final answer. This is how we inverse, right? So we left from A and identity, and we have obtained identity and A inversed. Therefore, what is A to the power of -1, so the inverse of my A matrix. It's the right side of this matrix that has remained after I created the identity matrix first. Therefore, it is 14 -8 -1 -17 10 1 -19 11 1. And this is your final answer. This is the inverse of A. And I know it's taken a little bit more time than probably you would have expected, but I've also explained what I was doing while I was doing it, so that's why it seems like longer. But this is how we create the inverse. I hope I didn't lose you guys. Let me know if this was clear enough, if you get what I did, if you have any questions. Clear? Great. If all is clear, then we will move on. From the inverse of the matrix to the last thing we'll discuss in chapter 2, the determinant of a matrix. So the determinant is actually a very pleasing exercise to work with because it's really easy. It only involves a little bit of calculus, but that's why we have calculators, right? So what is a determinant? A determinant is a function that assigns to each of the square matrices one specific number. The notation of the determinant is that of the name of the matrix, and it's got a few properties. And here we make the connection with the inverse of the matrix. For a non-singular matrix A, so a matrix that is invertible, we know that the determinant has to be different from 0. And if the determinant is different from 0, then we know that that matrix is non-singular. What can we deduce from here? That if A is a singular matrix, then its determinant will be equal to 0. Therefore, it will not be invertible. So if you're asked to check whether you can inverse a matrix or not, you first calculate the determinant. And if the determinant is equal to 0, the matrix cannot be invertible. If it is not equal to 0, so if it's different from 0, it means it has an inverse, and we can start looking for it. Let's see how we calculate the determinant of matrices. So for a matrix of 1 by 1, this is 1 by 1 means 1 column, 1 line, 1 element. It looks like this. The determinant of this matrix A will be the element inside the matrix. So determinant of A will be exactly the element in here between the brackets. Pretty easy. For a matrix of 2 by 2, so 2 lines, 2 columns, the determinant of such matrix will be calculated by the formula A multiplied by D minus B multiplied by C. A, B, C, D here from this equation matrix that I've written. Another easy way that I like to remember, because I never remember formulas, especially with determinants, because they're way too long, way too many. What I do is when I have to calculate the determinant of a 2 by 2 matrix, I do multiplication of diagonals minus multiplication of the other diagonal. And that is just as easy, and it's super correct. It's A multiplied by D, so the diagonal, minus the other diagonal, B multiplied by C. Now we have to calculate the determinant of a 3 by 3 matrix, and here is where the problem arises. A 3 by 3 matrix will have a determinant of such formula. It is A multiplied by E multiplied by I plus D multiplied by H multiplied by C plus all of these other terms that give us kind of like a headache, because there are way too many to remember and we have so many other things, important things to do. We do not exactly wish to memorize this formula. However, it is an option. I'm going to give you another version of how we can remember this formula for a 3 by 3 determinant. And it's your choice, whether you would like to remember the formula as it is or try to understand the algorithm I'm going to explain. It's not going to take long, but I do need you to pay a little bit more attention because I wish not to lose you. So remember, in a 2 by 2 matrix, I've told you that we do diagonal minus diagonal. I would like you to think about this 3 by 3 matrix kind of in the same way. we are going to do multiplications and summations of diagonals. And I'm going to start by pointing your attention here to the left first. This is the matrix A, B, C, D, E, F, G, H, I that we've seen before. In order to calculate or to create the formula of the determinant, we are going to multiply the diagonals, so A, E, and I, and we are going to add up to these diagonals the multiplication of the other ones. So the first diagonal is A multiplied by E multiplied by I, just like in our formula, to which we add plus diagonal DH multiplied D multiplied by H, multiplied by the opposite corner of this diagonal, so multiplied by C, as you've seen here represented by these colors. Okay, so here we have a green line and a green circle, to which we add the multiplication between the other diagonal, B multiplied by F, multiplied by the opposite corner, G. And we have come up to exactly the same formula as the one in the original determinant formula, only we've created it with diagonals instead. Remember, however, that you have to subtract something from it. What do you subtract? Exactly the opposite diagonals. So we're going to subtract diagonal C multiplied by E multiplied by G minus diagonal B multiplied by D multiplied by opposite corner, I, minus diagonal F multiplied by H multiplied by the opposite corner, which is A. And again, if you are to go and check, this is exactly what you should have obtained from the original determinant formula. I don't know which method you think is easier. Maybe you think just remembering the formula is a little bit easier. Maybe you think this algorithm makes a little bit more sense and you're going to use this one. It doesn't matter, because the final result is going to be the same. However, sometimes it is harder for me to remember the formula as it is, because there's a lot of A, B, C, D, E, F, Gs. So I tend to use this. It's your choice, however you think it suits your style best. That's the one that you should apply, because I promise you they're equivalent. They're exactly the same. As I've showed you, they yield the same formula in the end. So whatever you choose to create or to use is completely fine. We've explained now the determinant of the squared matrices, the ones that we use the most, so 1 by 1, 2 by 2, and 3 by 3. However, if it happens that you have to calculate the determinant of a n by n matrix, we have to apply the following formula, which theoretically is going to sound horrible, but trust me, we have an exercise immediately afterwards on which we will apply this, and we will see how we create these, how we actually work with this determinant matrix. So for an n by n matrix, n being more than 4 or equal to 4, we will choose a pivot line or a pivot row. So when you choose a pivot row, it means that you have to look through your matrix for a row that looks a little easier to calculate. Maybe has smaller numbers, maybe it's full of zeros, something like that. That's kind of what you want to look for. You will start creating your determinant according to this formula, which right now doesn't make sense, so I'm not going to explain it. I'll explain it once we're doing the exercise. But there is a formula that you apply in order to create your determinant, in which this A represents the position of the line, your pivot line, and these I plus J represent the indices of your position. Afterwards, you will calculate this another determinant of Aij, by basically cutting the rows the row and the line, the row and the column represented by the two indices, and working with the remaining coefficients as you were to work with a normal determinant of 3 by 3, 2 by 2, whatever. Let's do exercise 2.22 so I can better show you what I mean. And we're going to, where is it? I'm going to share the screen again from the book. And we're going to see what I mean. Okay. This is exercise 2.22 from the book. We are not going to work neither point A, neither point B, but we are going to work on point C. Why? Because it's the one that contains a 4x4 matrix. So it makes the most sense because I can apply all of the formulas that I've showed you before exactly on this matrix. So I will go ahead, write it down for myself so I can copy it into the whiteboard. If you want to do the same and work the exercise with me, you are more than welcome. Okay, and now we will move on to the whiteboard. So allow me to first copy down the matrix. C is equal to, it will be a matrix, which contains the numbers 1, 2, 0, 3. 2, 4, 0, 6. 0, 0, 1, 0. And lastly, -1, -3, 1, 0. This is our matrix. And we have to calculate determinant of C. So we have to calculate determinant of matrix C. Good. How do we start? Well, we start, the first step in our slides was to choose a pivot line. And I've told you the pivot line is the line that you choose so that it is the line that looks the easiest to calculate. It either has a lot of ones, zeros, or the smallest numbers. And I already see I have such a line in my matrix, and it's the third line, 0, 0, 1, 0. This is perfect. It has a lot of zeros, it contains a 1. It means that the calculus that I'm going to do with this line is going to be really easy. So my pivot line will be row 3. I'll write it down. Pivot line is R3 for me. I just wrote it down for myself so I don't forget. I don't necessarily need to write this down. Now I can actually start writing down the formula of the determinant. So the determinant of my C matrix will be, I told you that the formula starts with a -1 to the power of the summation of the indices of the line that I'm working on. Since I'm working on the third line, these are going to be the indices 3, 1, 3, 2, 3, 3, and 3, 4. These are the positions, right? So the positions of my elements. This is position 3, 1, 3, 2, 3, 3, and 3, 4. So these are the powers to which I'm going to raise my -1. The first power will be -1 to the first position to the power 3 plus 1. Multiplied by something which we call determinant C of 3, 1. I'll explain in a second. We're just writing theoretically now. Plus, again, -1 to the power of the next position. So this is position 3, 2. 3 plus 2. Multiplied by something called determinant of the position C32. Plus, I have -1 to the power position 33, 3 plus 3, multiplied by the determinant of the position C33, plus the last term, -1 to the power position 3 plus 4, multiplied by the determinant of something called position 3, 4. Okay? This is how it begins. We will now take care of the -1s because we have to see which one of the numbers are negative, which one of them are positive. So let's go ahead and take a look. -1 to the power of 4 will become a 1, which is a positive. It means that our determinant of C31 will be positive. So I have determinant of C31. Wait a second, I forgot something from the formula, I think. Yes, I apologize, guys. I'm going to go back on what I said earlier, and I'm sorry. inside the determinant formula, so -1 to the power of the position multiplied by the determinant, we also have to multiply each of the element with the element on that position. So it will be determinant of, so -1 to the power of the position multiplied by the determinant of the position, so determinant C31, multiplied by the element on that position, so the element of position 31, which is 0, plus -1 to the power of the position, so position 32, multiplied by the determinant of the position, so determinant of 32, multiplied by the element found on that position, so multiplied by 0, plus -1 to the position 3 plus 3, multiplied by the determinant of the position 3, multiplied by the element on that position, which is 1, plus -1 to the position 3, 4, multiplied by the determinant of that position 3, 4, multiplied by the element on that position, which is 0. And now you understand why we chose the pivot line, the ones with the most zeros and ones, because it helps us reduce the number of calculations that we have to do, right? And now I'll explain again from the beginning what we do with the ones. So the ones, basically, the -1 to the power of the position determine whether your determinant of C and the position has to be calculated as a negative or positive determinant. -1 to the power of 3 plus 1 is -1 to the power of 4. Negative to a positive power, to a even power, means positive. Therefore, what we're left with is determinant of C31. Multiplied by 0, however, yields a 0. Plus -1 to the position 3 plus 2 is -1 to the power of 5. -1 to an odd number will remain -1. Therefore, instead of a plus, I will actually have a minus. Minus the determinant of the position C32 multiplied by 0 will again yield a 0. Next one, -1 to the position 3 plus 3 will be -1 to the 6th, which is a 1, multiplied by the determinant of C33 multiplied by 1 will remain determinant of the position C33. Plus -1 to the power of 7 is -1, so I have a minus. Determinant of the position C34 multiplied by 0 will remain a 0. Therefore, what I actually have to calculate is determinant of the position C33. Now you're going to ask me, how do I calculate the determinant of a position? I don't understand. It's pretty easy. What you do is take your imaginary crayon or your imaginary pen, take a different color, and cut the line and the row corresponding to that position. If position is 3, 3, it means I have to cut the third line and the third column. So I don't cut them actually, I cut them theoretically. I pretend they are not there. And what I'm left with is 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers, which create my determinant of 3 by 3. So the determinant of C33 will actually yield into a determinant of the remaining numbers. So of 1, 2, and 3, because I cut the 0. Then I have a 2, 4, and 6, again, because I cut the 0. And then a -1, -3, and a 0, because I completely cut this line, and then I also cut the element on this position. And now I have to calculate the determinant of 3 by 3, for which I have a formula. It is 1 multiplied by 4 multiplied by 0 plus 2 multiplied by -3 multiplied by 3. If you're not understanding exactly, I memorized the formula, so I'm just working directly on it. Plus 2 multiplied by 6 multiplied by -1. Now I finished all the positive diagonals. I move on to the negative diagonals. These are 3 multiplied by 4 multiplied by -1 minus 2 multiplied by 2 multiplied by 0 is going to be 0 minus 6 multiplied by 1 multiplied by -3 is going to be -18. So minus 18 plus 18. And now I would have to go ahead and calculate. This is 0. This is -9 multiplied by 2 is -18. 2 times 6 minus 1 is -12. 3 by 4 multiplied by 1 is -1 is +12 plus 18. And the determinant will become 0. And this is how we work with determinants. This is probably the most complicated example I could have given you because I wanted you to see how we work with the 4x4 determinant and to understand how we calculate this determinant of the position. I hope it was pretty clear. If it weren't, I promise you I'm going to send you a little bit more material with a little bit more explained, like a little bit more detailed, this method of conduction. But yes, this is it for the determinant and for chapter 2 as it is. Do you guys have any questions on what we have done so far? So the -1 is part of the formula for calculating a determinant. So the -1 is there raised to the power of the coefficients in order to determine whether your determinant of the position will become a negative or a positive. It's part of the formula, so it doesn't appear just from somewhere. It's part of the formula, so that's how we have to write it. It's always going to be like that. It's -1 to the power of the position multiplied by the number of that on that position multiplied by the determinant of that position and so on. So the -0 and plus 18 at the end. This -0 and plus 18 come from, let me see. Okay, so when we start subtracting numbers from the determinant, the pattern we follow is -3 multiplied by 4 multiplied by -1 minus 2 multiplied by 2 multiplied by 0, which is where the 0 comes from, minus 1 multiplied by 6 multiplied by -3. 3 multiplied by 6 is 18, -18 because we have a -3. And because we had the negative sign in front of it, when you do negative, it becomes a plus. But I wrote it directly because it became a little lazy, so I wanted to write it directly. Yes, Ivo, you can do that, definitely. However, I'm not sure if it's going to be a more comfortable because it's going to take a lot of computations. But it's your choice. Yes, of course you can do it. How did you go from determinant C33 to the determinant of C? So determinant of C33 is the determinant of the position C33. The position C33 is exactly here where my lines intersect. And it means in order to be calculated, I have to cut away the line and the column corresponding to that position. Because the position is 3, I have to cut third row, third column, like we see here in red. After you cut them, you are left with basically a matrix of coefficients that form a 3x3 determinant. The ones of the coefficients remaining. So 1, 2, 3, 2, 4, 6, -1, -3, 0. Why? Again, because you cut away the line and the column corresponding to the determinant of the position 3. Do you understand? Yes, exactly. You would have gotten exactly the same answer if you would have chosen determinant. Actually, wait, give me a second. If you would have wanted to choose determinant of C22, you would have had to take pivot line, line 2. So everything that I've done here for the determinant of C, I've done according to the pivot line, row 3. If you would have done the determinant according to the second line, you would have had to do the exact sort of computations, only you would have had to create these determinants for the positions 2, 1, 2, 2, 2, 3, and 2, 4. You wouldn't have gotten to the exact same last last 3 lines of the equation. However, the final answer would have still been 0. But you would have had a lot of calculus to do. That's why when we choose a pivot line, we choose one that has the most zeros and the most ones, because look how beautifully they reduct. Otherwise, we would have had to create this determinant that you see here for all of the positions, for all of them. And it would have taken a really long time. That's why determinants of more than 4 by 4, including 4 by 4, are really timey to consummate, to calculate, because they take a lot of time. No problem. I hope it was all clear. Okay, guys. So this was it for chapter 2. I don't think I have anything else in my slides. Just one more property for the determinant of a matrix. This is a little bit of theory piece that you have to remember. So for any square matrix, because this is the only type of matrix that we can create a determinant for. So for any square matrix, we know the determinant of the transpose of the matrix will be equal to the determinant of the matrix. The determinant of A matrix multiplied by a B matrix will be equal to the multiplication of the independent determinants. And we know that the determinant of the inverse of a matrix will be equal to 1 over the determinant of that specific matrix. These are some properties. This is theory. So we have to know and remember this pretty well. And these exercises 224 and 225 will be for you to work at home. I will also send you the full algorithm of how to solve these exercises, like I did on WhatsApp earlier. But now I think it's time for a really short break. We're gonna do a 5-minute break, so everybody be back at 12:16. And we're gonna continue with chapter 3, which is the last chapter we're gonna do today. So we're going to speak about sequences with applications in finance. So everybody be back at 12:16 and we will continue. Okay, guys, I'm sorry to announce, but break over again. However, we don't have much left to go. We only have chapter 3, which is a short and easy chapter. So we're going to go through it really quickly. And I think, I'm not sure, but I think if you allow me, I'm going to take 10 more minutes at the end of the allotted 4 hours to just finish up a quick exercise at the end. I'm not exactly sure if that's going to be the case, but if it happens, please excuse me. Teaching on Zoom with Matrix is a little bit more complicated because I have a lot of computations to write by hand. So that's why I'm not exactly doing it on time, but I hope 10 minutes is not going to be a big problem. However, I'm not going to lose any more time speaking nonsense. Let's just move on to chapter 3. We're going to speak about sequences with applications in finance. At the end, we're going to speak a little bit about the applications in finance. You've already probably heard of these things like future value and present value, so I'm not going to extend too much into them. Let's go ahead. What is a sequence? A sequence or a finite sequence is represented by a row of numbers x1, x2, xn that are denoted by their position t. The position t takes the numbers. This mathematical representation means that t takes all the values from 1 to n, all the natural values. So 1, 2, 3, 4, until however long is n. They usually follow a logical pattern of deduction that helps us decipher the entire sequence. It means a logical pattern of deduction. It means that there is a rule that helps us understand how to find the next term of our sequence. They can be written either as lines of numbers, so x1, x2, xn, or they can be represented graphically, which we're not going to spend too much time on with the graphical representation. I have an exercise prepared for you to do at home. We won't do it in class, but I'll show you how it's done. So let's take a look at what a sequence is and how it looks like. So I am going to point you towards exercise 3.1 from the book. We have this exercise right here. We won't do it all. I just wish to show you 1 or 2 examples so that you understand kind of what a sequence looks like. Let's take a look at exercise A. We have the sequence 1, 4, 7, 10, 13, 16, and so on. It should be continued, you know, like it goes on until it doesn't go on anymore. How do we determine the rule of this sequence? Because it asks us find a formula type notation for the following sequences. So let's go ahead to the whiteboard. And I forgot where my sequence exercise was, but I'll find it in a second. Over here, our sequence is 1, 4, 7, 10, 13, 16, and so on. What is the rule? So, more so, how can I determine a formula that helps me calculate the next number in this sequence according to the position of the number in the sequence? Think about these 1, 4, 7, 10, 13, 16 as numbers in a sequence. X1 is equal to 1, X2 is equal to 4, X3 is equal to 7, X4 is equal to 10. And I think that's more than enough for you to get the idea of what I mean. So you see that each of these numbers is attributed to an X, and this X varies from 1 until n, which is the last term in our sequence. We have to find a formula that includes this number, this indice of my X, so that it makes sense when we're calculating the next number in the sequence. Okay. We can, determining formulas for sequences is not really the scope of what we're going to do in chapter 3. I just would like to show you an example of how it looks like. So I thought about this exercise a little bit, and I noticed an interesting pattern that concerns the indice of each of these x's. I noticed that if I were to multiply the indice by 3, so 3 multiplied by 1, and then subtract 2 from this notation, I will always get the next number in the sequence. Example, 3 multiplied by 1 minus 2 is equal to 1. 3 multiplied by 2, that is 6, minus 2 is equal to 4. 3 multiplied by 3, that is 9, minus 2 is equal to 7. 3 multiplied by 4, that is 12, minus 2 is equal to 10, and so on. Therefore, the rule of my sequence will become, I will call t is equal to 1, 2, 3, all the numbers until n. Therefore, the rule will be x t will be equal to 3 multiplied by t minus 2. And this is the rule of how I obtain the next number in my sequence. And this is pretty much all you have to understand about how to form these sequences like this. From here on, we will actually go into a little bit more in depth with the arithmetic and geometric sequences. But more generally, this is what we do. So this has been an example. I would like to ask you if you'd like to practice more with these exercises. I recommend you do exercises 3.1 and 3.2 from the book. They're really good, and they can allow you to play a little bit with rules and sequences as it is. Now we will move on to the arithmetic sequence, however, which is more important for our study. We call a sequence arithmetic if the difference between any two consecutive numbers in the sequence is constant. So the difference between x of t plus 1 minus x of t is always going to be equal to v, which is a constant, which we also call the difference of the arithmetic sequence. What does this mean? If we have a constant number, a constant value that can be found between two consecutive values of my sequence, it means that I can rewrite the arithmetic sequence according to a formula, and it is always going to be written according to this formula. xt, so the x, the value of the sequence that I'm looking for, the term of the sequence that I'm looking for right now, will be written in terms of the first value of the sequence, x1, plus t minus 1, so the indice t minus 1, multiplied by the constant v. And this is going to be a formula for all of the arithmetic sequences that we're going to work with from now on. Let's take it a step further and also learn about the sum of the arithmetic sequence, because most of the exercises and most of the applications of sequences will not ask you to just find random sequences of numbers for nothing. They want you to probably calculate something because they are either interest on a mortgage, or they want you to calculate profits monthly because maybe the profits gather up in an arithmetic sequential way, so on. So we have to know how to calculate the sum of the arithmetic sequence. There are two possibilities. They are both equally correct. The only difference between the two formulas is that sometimes you have some parts of the information, sometimes you don't. What do I mean? We see the first formula is 1 divided by 2 multiplied by n, which is the number of numbers in the sequence, multiplied by the first term plus the last term. Or we can also calculate it as the number of numbers multiplied by the first term plus n multiplied by n minus 1 multiplied by the constant v, everything divided by 2. These are two equivalent equations. And again, the only difference between when we use them is, for example, if I were to know from the beginning both the initial value and the last value, it would make a lot more sense for me to use the first formula because I don't have to calculate anything else. However, if I'm not told the last value, only the initial value, which is what happens most of the times, and I know the constant between the constant difference between the values, then I can simply apply the second formula without having to trouble myself too much with also calculating the last value of the sequence and so on. So again, these are equivalent and you use them depending on the situation, whichever fits better. Now we can actually work. We're going to do exercise 3.5 and 3.8. It's actually the same exercise, and it asks us to once calculate the sequence, and then it asks us to calculate the sum of the sequence. So that's what we're going to do. So exercise 3.5. this exercise right here. Of an arithmetic sequence, the first three numbers are 50, 55, and 60. So x1 is 50, x2 is 55, x3 is 60. And we are asked to determine x 250. Let's go ahead. So the first three numbers are, I'm going to write them. X1 is equal to 50, x2 is equal to 55, x3 is equal to 60. What is x 250? The first step that I have to do is remember the formula of how to calculate any term of any arithmetic sequence. Okay, so an arithmetic sequence will be the term of any arithmetic sequence, x of t, will be calculated as the initial x, so x1, plus t minus 1 multiplied by the constant v. Good. Now comes the question, is this actually an arithmetic sequence? Can I actually apply this formula? Well, it's very easy for me to understand if I just do the difference between two of the consecutive terms in the sequence, and I obtain the same difference no matter how many others I differentiate, let's say. How do I find this out? I'm going to try x3 minus x2. This is going to yield 60 minus 55, which is 5. Is this going to be equal to x2 minus x1, which is going to be 55 minus 50, which is equal to 5? Yes, it is, because I have a constant difference between the consecutive terms of my sequence. It means this is an arithmetic sequence indeed. And it also means that my constant v is equal to 5. Great. Do I have now all of the information in order to calculate x of 250? Yes, I do. X of 250 will be calculated as x1, which is 50, given by the exercise, plus t minus 1. T is the position of my variable that I have to find out. So t minus 1, which is 250, minus 1, multiplied by the constant v, which is 5, should yield the value 1295, which is the exactly 250th term in my sequence. And this is the value that you should obtain. And this is how we do exercise 3.5. Now, after creating the sequence, let me quickly look through the exercise because I forgot exactly how many we have to calculate, but I think, okay. Part 2 of this exact same exercise is asking us to calculate, so the sum of the first 20 elements of the sequence. How do I calculate the sum of the first 20 elements? So I have to calculate S of 20 is equal to, I remember I have two formulas that help me calculate an arithmetic sequence. So the two formulas that I can use are either this one or this one. In my case, knowing that I do not have x20 because that is the last term in my sequence, when they ask me to calculate the first 20 elements of my sequence, it means that the last term will be x20, right? I don't have x20, so I would have to calculate it. So I'm too lazy to calculate it. I don't want to. So therefore, I will apply the second formula just because I don't have to take an extra step to calculate another variable when I can just go ahead and write according to this formula right here. So I'm going to apply n multiplied by the first term plus n multiplied by n minus 1v divided by 2. And the whiteboard, S20 will be equal to n, which is the number of numbers, which is 20, multiplied by the first term of my sequence, which is this x1 is equal to 50, multiplied by 50. Plus, now I have a division. I have n multiplied by n minus 1, so that is 20, multiplied by n minus 1 is 19, multiplied by the constant difference, which is 5, everything divided by 2. So the sum of this arithmetic sequence of the first 20 numbers should be, here we have 10, 0, 0. Plus here we have 190 multiplied by 5. I think I'm just gonna go ahead and look for the final answer because I don't have a calculator on hand, but we should obtain 1,950. So this should be our final answer. And yeah, that's it. This is how we work with the arithmetic and with the arithmetic sequence and the arithmetic sum. I hope this was clear enough, but let me know, guys, if you have any questions on what I did, on the exercise, on the formulas, or anything else. Okay, so this part doesn't really have vectors. No. We're slowly stepping away from vectors for just a little bit until chapter 4. When we're going to be speaking of Markov chains, which are really easy to understand, they're applied matrices. We'll see. But no, this part we're taking a break. We're just doing beautiful algebra, little easier. At least in my opinion, I think this is a little easier. Also matrices, I don't know what you guys think, especially after seeing the systems and working with them a little bit, but I don't think the systems and that part of the matrices are necessarily hard. I think they're doable. I think of course, they take a little bit of practice and there's some formulas that we have to remember, but I don't think they're particularly hard. I think mathematics 1 was much harder, in my opinion. Okay. So if there are no more questions on what we have done now, we will move on to an application of the arithmetic sequence, which is the linear mortgage. And we will use exercise 3.6 from the book to understand what this application is all about, because there are no actual formulas or rules that we follow. So we'll simply apply it directly on an exercise. So let's see, exercise 3.6. This exercise right here. We are told that someone buys a house for 300,000 euros. The buyer decides to take a linear mortgage where the mortgage is paid back in 20 years. A linear mortgage means that the person who buys the house has to pay back each year the value of the debt divided by how many years they have to pay for the debt. That's how much money they have to pay yearly back. We are asked to determine the sequence that represents the interest payments if the interest rate is equal to 5% in all of those years. Great, that's what we have to do. So we have to find the sequence, and I will also tell you that I'm going to give you like a few examples of the sequence first, because it's 20 years, it's a lot. We can't write it all down. But we remember the exercise. I have it also here written down, so let's move on to the whiteboard. How do we create an arithmetic sequence for a linear mortgage? We are told that we buy a house for 300,000 euros. We have 20 years to pay it off, and we have a 5% interest rate. Because of course we have an interest rate, right? How should this look like? How do we put this exercise in a more maybe easily accessible way? I would say that the best thing that we can do is write it down as a table, which includes the year, the mortgage amount, and the amount of the interest payments that we have to do. And these years will be year 0, year 1, year 2, year 3. I'm going to have many years until my 20th year when I will finally have paid off the mortgage. In my first year, my mortgage amount is 300,000 and my interest amount is 0 because I had just gotten the mortgage, so I don't have to pay interest yet. I pay interest 1 year afterwards. Great. How do we determine from here on what we do? Well, the first thing that we should do is calculate the amount of the mortgage that we're going to pay off yearly. How do we do this? We calculate it by, so amount per year will literally be the amount of the mortgage, so 300,000 divided by how many years we have to pay for the mortgage, right? So this calculus will be 0015 and then 1230, so 15,000 per year. That's how much money we have to give back yearly without interest. The interest, however, how do I calculate it? How much money is my interest? Does anybody know? We can also deduct it from finance if we remember a little bit. But if not, I will tell you that in order to calculate the amount of interest that you need to pay back yearly, you do 5%, which is the interest rate that they have assigned you, 5% of the value of the mortgage. So 5% of 300,000. 5% of 300,000 euros will coincidentally also be 15,000 that we have to pay off in the first year. Great. Let's already put some of this information into context. So year 1 year after we have taken the mortgage, we have to pay off 15,000 back to the bank from the 300,000, leaving us with 300,000 minus 15,000, which is 285,000 euros left to pay. But we also know that we have paid interest, the 5% yearly, of the value of the mortgage, of the value of the mortgage from the year before. So 1 year after I had taken the mortgage, I have to pay interest in the amount of 5% of 300,000, which is 15,000. What happens then the year after? The year after, my mortgage will go down once more by 15,000 because that's how much money I have to pay yearly. So it will go down again by 15,000, which will yield 270,000, if I'm not mistaken. I think this should be correct. But how much interest do I pay? Do I pay another 15,000 of interest? No, because the interest rate will adjust to the amount of mortgage that I have left to pay. So what I will pay 5% of will be the amount of mortgage from the year 1. So it will be 0.05 multiplied by 285,000, which will be 14,250 euros. That's how much money I will pay in interest in the second year. What about the third year? Again, my mortgage will go down by 15,000. So I will go ahead and write again 270,000 minus 15,000. That is 255,000 in mortgage left. And in interest, I will have 5% of 270,000, 0.05 multiplied by 270,000, which will be 13,500, and so on. In year 20, so in my last year of the mortgage, my mortgage will have been paid off because for 20 years constantly I kept subtracting 15,000 from my initial mortgage of 300,000. So in the last year of my mortgage payment will be 0, and my interest payment will be my constant V that I had taken from my arithmetic sequence. Why? My interest payments in a linear mortgage become an arithmetic sequence, and you can check this by subtracting any two consecutive numbers. Year 3 minus year 2 gives you minus 750. Year 2 minus year 1 gives you minus 750. Therefore, the last interest payment that I will make in my last year of the mortgage will become 750 euros, which is the amount of money that I owe back from interest to the bank, which will be equal basically to the positive constant V. Why is it positive and not negative? Because we evidently cannot give back negative money. It's money that we owe. That's the representation of the negative sign in this context. But this money is the money that we owe as interest back to the bank after all of these years of paying back the mortgage at a 5% interest rate. Therefore, the arithmetic sequence that they are asking us to determine, the arithmetic sequence will therefore be 15,000, 14,250, 13,500, and so on. And the last term of your arithmetic sequence will be 750. And this is it. We can also calculate the sum and so on according to the formula that we've learned before. But I'm not going to waste much time on it because it's just applying the formula and calculating the arithmetic sequence. So I'll give you that to do as homework for at home. Let me know what you've obtained, of course. So this is it, the application of the linear mortgage, basically the application of the arithmetic sequence into linear mortgages. I hope that was clear enough. I also know that probably you've seen these things before, so it's probably not the hardest part of the mathematics that we're doing right now, but let me know if you guys understood and if it was okay. And then we can move on to the geometric sequence. Understood? Okay, perfect. Let's speak about the geometric sequence then. So we are already acquainted to the arithmetic sequence. So let's see what the deal is with the geometric sequence. So sequence is called geometric if the quotient, so not the difference, but the quotient of any two consecutive numbers is this in the sequence is constant. What is the quotient? It means the ratio obtained by division. So by dividing x2 by doing xt divided by xt minus 1, we obtain the quotient r. That's how we obtain it, okay? R, therefore, is a constant, also known as the geometric ratio. If a sequence is geometric, so it has this constant quotient, we can rewrite the geometric sequence according to the formula xt is equal to x0. So the initial value, this time the values start from 0, they don't start from 1 anymore, multiplied by the quotient to the power of the element in the sequence. Remember, we had a similar formula for the arithmetic sequence, only it contained summations and stuff. Here we have multiplication. And let's see. Exercises 3.9, 3.10 I have written here. Let me see what they look like. What can we do from them? Oh, these are just some practice exercises that I wanted to share with you in order to understand a little bit more about the geometric sequence. Which one? Okay, we're going to do exercise 3.9. No, actually, I'm going to ask you to do exercise 3.9 by yourselves at home. This is just to check whether the sequences are geometric or not. So what you have to do is determine the sequence according to the formula and then try to calculate the quotient, the ratio. If you get a constant ratio, it means it's geometric. If you don't, it's not geometric. And we will do exercise 3.10 together. So, of a geometric sequence, it is given that x1 is equal to 108 and x4 is equal to 32. We have to determine the geometric ratio and then to determine x25. Let's go to the whiteboard and we're going to write down. So we know x1 is equal to 108 and x4 is equal to 32. We are asked to determine x25. and the ratio r. How do we start? We are told that these numbers are forming a geometric sequence, so I don't have to check for the sequence coherence or not, because I'm already told this is a geometric sequence, so it's fine. I can already work with it. And I can start by writing down the formula of how to calculate any term of the geometric sequence. Xt is equal to, where is it? X0 multiplied by the ratio to the power of the indice t. All right? So, because here, give me a second, guys, because I think this is the exercise that I was, yes. Okay. So the first thing that we notice about this exercise is that the formula starts with xt is equal to x0 multiplied by the ratio r to the power of t. We do not have x0 in this exercise. We have x1. Therefore, we will have to modify our formula in order to calculate this xt according to x1. I will first show you how we would do if this were x0. And then afterwards, I will ask you to work together and calculate how do we change the formula in order to also attribute x1 into this calculation. So we'll pretend this is actually x0. If this were x0 and this is x4, oh, no. Guys, I'm sorry. I made some notes on my notebook and I don't understand what I read. So I need a second because I don't understand what I had done, which is very unprofessional. So I'm really sorry about that. But I'm a little tired right now, so I'm not thinking very straight because of it. Okay. Is it? Okay. I don't know exactly what I had written on my notebook. I'm a little confused right now, but it's all good to go. We can move on with the exercise. I'm really sorry. I'm just a little bit tired. Okay, great. So the first thing that we have to do when we're calculating this exercise, we have to find the sort of connection between x1 and x4 so we can actually calculate the ratio r. So I will try to think about the formula that I can apply in order to calculate each one of the x's. And I will start with x2. If this is a geometric sequence, it means that I can actually obtain x2 by multiplying r with the previous x, right? So it's x2 is equal to r multiplied by x1, which means that I can also calculate x3 in the same way. I can calculate it as r multiplied by x2. However, I don't know x2. So how do I calculate it? I will rewrite it as r multiplied by, what does actually r to mean? R multiplied by r1, by x1, like that, which will yield r to the power of 2 multiplied by x1. Same thing will happen with x4. x4 will therefore be r multiplied by x3, which is actually equal to r multiplied by r to the second power, multiplied by x1, which again is actually r to the power of 3 multiplied by x1. Luck made it that we actually have the value for x4. We know x4 is equal to 32. And we actually also know x1 is equal to 108. Therefore, I can rewrite this equation as 32 is equal to r to the power of 3 multiplied by x1, which is 108, right? What do I do in this situation? I will go ahead and write 32 divided by 108 will actually become r to the power of 3. 32 divided by 8 is equal to r to the power of 3. Can we reduce this further? Yes, we can. If we reduce this by 2, no, we can reduce it by 4 directly. We will obtain as a final result 8 divided by 27. Because 8 times 4 gives us 32 and 4 times 27 gives us 108. I divided this, I simplified this fraction by 4 in order to obtain the much simpler version, 8 divided by 27, right? And this is equal to r to the power of 3. Now, do I know a cube that can satisfy this relationship between 8, 27 and r to the power of 3? Yes, I actually do know. I know that 2 to the power of 2 is equal to 8. 2 to the power of 3 is equal to 8. And 3 to the power of 3 is equal to 27. Therefore, r will be equal to 2 divided by 3. So this is the ratio that we're looking for. This is our r. Correct? Yes. Good. Now, what we can actually do is calculate x0, because we need x0 in this context. How do we calculate x0? We have the formula xt is equal to x0 multiplied by r to the power of t. And we are going to make use of x1 in order to understand this, okay? Oh, wait, some questions in the chat. How did you do the 2 divided by 3? This is basically, what is this called? Square root. Well, actually, it's not square root. It's a root of the power of 3 of 8 divided by 27. Yes, you can do it on a calculator. You just have to make sure that you don't do square root as if it were a power raised to the power of 2, but as if it were raised to the power of 3. I am lacking a little bit of, like my memory is lacking right now how that is called in English, but I will make sure I remember. This is basically this, what you have to do. Like that. To the power of 1, yes, that's exactly it. It's 8 divided by 27 to the power of 1 divided by 3, or this root, like cubed root of 8 divided by 27. And this is equal to 2 divided by 3. But you do this on the calculator. I did it in my head, but you do this on the calculator, okay? Okay. Great. So now we go on. We will calculate x0 by introducing the formula x1 is equal to x0 multiplied by the r to the power of 1. Why? Because this is the indice of the x1. How much is this? 108, that is the value of x1, will be equal to x0, which we have to calculate because we don't know it, multiplied by 2 divided by 3. Like that. Which means that our x0 should be equal to, I think it is 108 multiplied by 3 divided by 2. I think. Let me check my calculator. 108 multiplied by 3 divided by 2. 162 multiplied by... Yes, this is correct. So it should give us 108 multiplied by 3 divided by 2, 162. This is x0. Now that we have x0, we can actually go ahead and calculate what they wanted us to do, which is x25. How much is x25? X25 will actually be x0 multiplied by r, which will be raised to the power of 25. How much is x25 going to be then? x0, which is 162, multiplied by This is 2, I'm going to write in a parenthesis, 2 divided by 3 raised to the power of 25. If you want to be fancy, you can rewrite this 162 as 108, which is x1, multiplied by 3 divided by 2, multiplied by 2 divided by 3, everything to the power of 25. You can take 3 divided by 2 and write it as 2 divided by 3, everything to the power of -1, and therefore this will become x25 is equal to 108 multiplied by 2 by 3 by 3 to the power of 24. I just wrote a few of the ways that x25 can be rewritten as, just to show you. I don't know exactly how the answer would look like at the end of the book, but no matter what answer you get at the end of the book, these are all equivalent, okay? That's my point with this rewriting of the exercises. But yes, this has been the geometric sequence with its application. And I hope it was I hope you guys understood it. Okay? The next thing that we have to quickly go through is the sum of the geometric sequence, which only has one formula written right here as x0, so the initial value x0, multiplied by 1 minus the ratio to the power of n plus 1, divided by 1 minus the ratio. So this is the formula we're going to use for the geometric sequence from now on. And we can also do an exercise on this sum of the geometric sequence. However, it's just an application of the formula. So I would ask you to try to do it at home. If you cannot do it, I will send you something on WhatsApp and we can discuss it at the beginning of our next lesson. But it's just an application of the sum, so it shouldn't be too hard. Because I would also like to quickly go through the present future value and annuity mortgage before we end our session for today. So we already have heard a little bit about these notations from finance. Let me quickly go through them again. The present value is an amount of money that you need today in order to obtain a certain K amount in the future at a specified interest rate after a certain number of years. The formula should be present value is equal to K, so the amount, multiplied by 1 plus interest rate to the power of minus t. You can rewrite this as K divided by the 1 plus interest rate to the power of t is the same thing. Future value, however, the value of an amount of money K after several years in the future. So I know I have K amount of money today, and I would like to see how much money am I going to make out of this amount in the future. Therefore, the only thing that changes from the present value to the future value formula is the power of the number of years. Here we had it to the negative, here we had it to the positive. Except for that, everything else stays the same. The last thing, the annuity mortgage. So in an annuity mortgage exercises, we are usually expected to calculate the amount of money we own the bank yearly. So an annuity mortgage, basically what we have to calculate is this amount of money that is considered to be the amount of money of the mortgage plus the interest already included in the calculation. The general formula is A, which is the amount of money we owe, will be calculated as the amount of money originally debted to the bank, so the mortgage, multiplied by 1 plus interest rate to the number of years we have to pay, multiplied by 1 minus 1 plus the interest rate, everything divided by 1 minus 1 plus the interest rate to the power of the number of years that we have to pay the mortgage for. I've also written here down what the debt I and N mean in case you forget when you're doing exercises on your own. And for the annuity mortgage, we have another exercise I would actually like to work with you, which is the last exercise we're going to work today together. And let me find it. Okay. And I think it should be exercise 316 from the book. I think that's the exercise they wanted to work. Yes, that's the exercise. And I promise you after this exercise, I'm letting you go and we'll see each other tomorrow. But I really want to work this exercise with you guys. So it's this exercise right here. Okay. I hope everybody can see it. We'll read it all together and then we'll solve it on the whiteboard. A couple buys a house for 300,000 euros and they take an annuity mortgage with a term of 30 years and an interest rate of 4% to pay back the house. So what do we know? Debt is equal to 300,000, N is equal to 30, and interest rate I is 4%. The repayments are done in yearly fixed amounts. We are asked to determine the yearly amount the couple has to repay to the bank. And then we are asked to determine the total amount of interest the couple has paid at the end of the mortgage term. Great, let's do that. Whiteboard. And we'll compute. So we know debt is equal to 300,000, N is equal to 30 years, and the interest rate I is equal to 4%. How do we calculate the amount of money that we owe back the bank? It's the formula. I'm not going to write it on the whiteboard because it's really complicated to write these many equations on the whiteboard without them being a little too weird. So I would like to ask you to please write down the formula now so I can work with you at the same time as I'm writing the information on my whiteboard, okay? So we have the amount of money is going to be the debt multiplied by 1 plus interest rate to the power of N, multiplied by 1 minus 1 plus the interest rate, everything divided by 1 minus 1 plus the interest rate, everything to the power of N, okay? I'll give you a couple more seconds. Okay, let's go back. What is A? I'm going to write down directly the actual numbers now. So 300,000, which is the value of our debt, has to be multiplied by 1 plus the interest rate raised to the power of 30. So 1 plus 0.04 will be 1.04 to the power 30 multiplied by 1 minus 1 minus parentheses 1 plus the interest rate will be 1 minus 1 minus the interest rate. So I'm going to write directly multiplied by negative 0.04 because that's what you would get from that subtraction. And this entire scheme of numbers, actually I'm going to put squared parentheses, has to be divided by 1. I'm going to write it in parentheses, has to be divided by 1 minus 1.04 to the power of 30. Pay attention, not the entire parentheses is to the power of 30, but only 1.04. That is it. Okay? Great. What do we obtain? All of this calculus will be made on your calculator. We do not make this kind of calculus by hand. The important thing is that in the end, we obtain 17,349.03 euros per year that we owe the bank. We have to give back to the bank. What is this money? This money is mortgage plus interest payments. So this money contains both the amount of the mortgage plus the amount of the interest payments. And this is the money that we owe yearly. So this is what the exercise has asked us to calculate in part A. What about part B? In part B, they ask us to specifically calculate only the amount, the total amount of the interest. How do I calculate the total amount of the interest? Really easy. From the amount of money that I have to pay back yearly, from A, I will multiply it by the number of years that I've been paying my mortgage for, and I will subtract the amount of the debt. This is how I calculate total interest. So A multiplied by N minus debt. What do I obtain? 17,349 euros, multiplied by 30 years, from which I subtract the amount of money that I owe the bank initially. And I will give you directly the final answer, which should be 220,470.89, I think I wrote, which is 220,470.89 euros that I pay only in interest on top of the amount of the mortgage that I pay back to the bank. And this is an annuity mortgage exercise, and this is how we work with it. And this has been literally the end of our class. I hope this was understandable. So let me know, guys, if you have any questions now before we stop the meeting. I hope this was, I know it wasn't easy because we've been here for 4 hours and I've thrown a lot of information out at you. But if you don't have any questions, I would like to do a quick recap of what we've done today, so I can explain to you what I'm going to do tomorrow. And yeah, so let me know if you have any other questions.